Last session we left off with a population of bacteria that was doubling, and we built a model and did a little bit of work with that. And I want to just reiterate a couple of items on that regarding doubling time, and then we want to continue on today talking about application and logarithmic models. So you're feeling pretty good about this. You can use these in science courses, in chemistry classes, in biology, where you're dealing with population growth or maybe radioactive decay in a chemistry course. You can use it in finance and business where you're, say, paying off a loan over time, or you actually have an investment that is growing over time exponentially. And so you use exponential mathematics and the mathematics of logarithms to then build those kind of models to have that understanding. So take this with you into other subject areas and try not to forget it, okay? So let's go back here to the last session. We had 1 billion bacteria, and remember that's 1,000 million bacteria. So it's 10 to the 9th initially, and that I'm going to label as the initial population of bacteria. Oftentimes, for an initial value, we use a little subscript with a little 0 there. Sometimes we call that naught. B naught is you in the language, so you'll hear other instructors using that vocabulary. We said that the population, we started with 1 billion bacteria, and then someone suggested that we let this population double in 13 hours. So what we did in last session is we built a model as a function of time. Bacteria as a function of time was equal to the initial population, B naught, and then we used a base of 2, and we raised that to the time divided by 13. And the reason we did that for the is because when we put in, well, let's do this first. If we put in 0 for time, that means that'd be the start of our experiment. With 0 in for time, then we have the initial population here times 2 raised to the 0 power. And that turns obviously to 1, and so we end up with that value, that initial value is B naught, which you see right here in the model. At 13 hours, then we have that initial population times 2 raised to the 13 over 13, which is just 2 to the first power, so that's equal to B naught times 2, or in the case of our initial population being 1 billion, then we end up with 2 times 10 to the 9th, and so 2 billion after 13 hours. The model we had as a graph then is the population as a function of time in hours. After 13 hours, the population is 2 billion, and initially it was 1 billion, or 10 to the 9th here, and then 2 times 10 to the 9th there. And we know from our background with exponentials that the function curves upward. It's not a straight line. It's not a straight line. It gets steeper and steeper the further out you go. Okay, the reason I wanted to start with that today, even though we went through this yesterday, let me just first of all see if anybody has any questions about that. Any questions? Okay. Let's say instead that we knew the tripling time of something. Say the tripling time is, say, 6 hours. So let's do this. Actually, I'm just going to go ahead and put it down below here. Let's say we're talking about apples. The population of apples that I pull off the tree triples in 6 hours. From when I started. That's not a very good example, is it? Let's use money. Okay, let's say we have How much money to start with? Keep it small.
$100.
$100, okay. So let's say we're talking about money. So let's call it a M function of time, and this is an investment. So let's say we start with $100. If we start with $100, that's our initial amount. And let's say we know it triple. Let's not use 6 hours. Let's say, that would be kind of nice. Let's say it triples in
6 years.
6 years, okay? 6 years, okay? So let's say it triples in 6 years. So what exponent would you put on 3 to build the model? T over 6. T over 6. Because if you put in 6 years for t, then this becomes 3 to the first power, and you're going to end up with $300. Okay? So that's an easy way, if you have a piece of information about your initial population or initial amount, in this case $100, then you can build a model if you have some information about either doubling time like we did with the bacteria, or tripling time in this case. Okay? So let's take a look. Let me go ahead and put this in here. Let's say we put in our 6 years, and then our amount of money we're going to have is going to be 100 times 3 to the 6 over 6, $300. A graph of that, very simple. You're starting with $100, and it's going to grow after 6 years. This is time in years. It's going to grow to 3 times that. Try to get in the habit of drawing your sketches relatively to scale. Relatively to scale. So the graph is going to rise like that to $300 in 6 years, that model. Any questions on that? Not too bad, is it? Okay, here's a question for you. Let's say we have this money model right here with $100 invested, should be 6 years. Let me ask, when is it going to be worth, say, $200? Okay, when will this model be worth $200? Now, if you look at your graphics in here, 200 here. If this is 100, 200, 300, it's going to be right over here, and it's going to be that value of time when this becomes 200, right? This is what we're looking for, right there, that value of time. Make sense graphically? Everybody okay? All right. So what we could do is we could just put this in our graphing calculator, couldn't we? Couldn't we? And then we could just trace over until we found the y value equals 200 and read off what that amount of time is, how many years it took to grow to 200. Okay? This would be the same as this if this was 100 or 100 million or 100 billion. Okay,
Could
that kind of.
Just put 200 in for y and solve it?
Yes, and that's how we would do. And so what I wanted to first of all comment on is how you would interpret this graphically with your calculator or just by a hand sketch here. You know you're going to come up with an answer something less than 6 years. And so now let's go ahead and actually do the algebra like Melissa suggested. We are going to let m of t equal $200. That was our question. When will this grow to $200? So this future value is going to be 200, and we need to figure out this value of time right here. Our model is 100 times 3 to the t over 6 equals now m of t. Okay? Everybody with me? So, first step, somebody near the back of the room. Divide both sides by 100. Why do you suggest that we divide both sides by 100?
Don't you want to get t by itself?
We want to isolate the exponential. Okay, so when you write an exponential equation, you want to now isolate the exponential. So we divide both sides by 100, so we get 3 to the t over 6 is equal to 2. Now somebody in the back row suggests, what's the next step?
Take the log of each side.
Kyle, take the log of both sides. What base do you want to use?
Let's do ln.
ln, natural
Natural
logarithm, base e. So let's take the natural log of both sides. T over 6 is equal to the natural log of 2. Everybody okay? Let me put this down. And so then, Kyle, help me one next step.
You pull out the exponent.
Pull out the exponent in front by the power rule. Remember that? The power rule. So t over 6 times the natural log of 3 is equal to the natural log of 2. We now would multiply, there's two ways you can say this or do this. We could divide both sides by the natural log of 3, and that would bring this natural log of 3 off the left side and put it as a denominator on the right. And then we'd multiply both sides by 6, right? But we could also interpret this as, instead of what we could do, is we could multiply both reciprocal of what's attached to t. The reciprocal of what's attached to t is 6 divided by the natural log of 3. So if we multiply both sides of this equation by 6 over natural log of 3, both sides, remember, that's a little one-step way of isolating t. So then t's actual value is going to be 6 natural log of 2 over natural log of 3. You could, at this point, turn on your calculator and punch this, or what could you do before you turned your calculator on? Just for practice with logarithms. Here's your hint.
Put that in the exponent.
Kick this back up as the exponent on the 2. 2 to the 6th is, you should know this, 2 to the 5th is 32. So 2 to the 6th is 2 times 32 is 64. So what we get here is the natural log of 64 divided by the natural log of 3. And what do you get? You better get an answer. Think back here to what we did graphically. We better get an answer something less than 6. And what do you pick up? Calculator.
3.785.
3.785, so about 3.79, roughly 3.8 years. 3.8 years. So here is your exact answers in this format, and there's your approximate answer, about 3.8 years. So what we did is we built ourselves a simple model by knowing a piece of information about the initial amount invested. Could be $100, $100,000, $100 million, whatever it might be, and it's tripling in 6 years, and then we were figuring out when the amount of money would grow, how much time would it take for it to grow to 200. And there's our result. Okay? So that's a pretty good example. Let's take an example out of the book now. There was a pair of problems in a couple different sections of the book, and I'll just verbalize what they are for you if you don't have the book in front of you. On page 282, number 98, is a model, another exponential model, that is the area of a wound. Let's say you fell off your bicycle and got a big old scrape on your elbow, okay? So you have a wound of a certain size. So the area of the wound, as a function of days, because we know what happens with a scrape is it will gradually heal up, and they usually heal up from the outside and from below, underneath. We don't see that part, but we do see the outer edge. So the area is going to decrease over time. So it starts out with some initial area. And they actually give us a model in this particular problem. They say it's a base E exponential to the negative 0.35 n, where n is in days. When you see a negative exponent on an exponential where the base is bigger than 1, it's going to graph how? Always. Good, Jennifer. It's going to be a decay exponential that's going to come down from this initial value over time, eventually heading towards a horizontal asymptote of 0. So here's the area as a function of days, where days is the variable n. So this problem in the textbook asks, first of all, what's the size after 3 days? And so what we're going to do is we're simply going to put in 3 as the input value. This is really easy. So here's the initial size, e to the minus 0.35, and we put our 3 in there for the number of days. And then we'll punch that on the calculator in a moment. It also asks in part B, what's the size after 10 days? So it's the initial area times e to the minus 0.35 times 10. Where would this information in these two statements, oh, actually, let me write that down. Here's the part A here. Part B was asking the size after 10 days. Okay, so where would this information be up here on this picture?
A.
Jerome?
A would be close to the y-axis, and B would be closer.
Okay, where would we find 3 and 10? This is really basic.
Yeah, that's right.
Go out to the right, right? Go out, and then this is going to be the value at 3, the height right there, and then we're going to go out to 10, and the height right there, right, is going to be the value there. Okay, the output value there, the size of the wound. Feeling good? Everybody see the model? So the model is going to decrease in size as time passes. So we'll punch that up in a couple minutes. Let's go on now to another page in the book where they take this same model. This is problem 120 now on page 296, where it asks the following questions. How many days, in part A, how many days, n is unknown, for the population to become half of what it originally was? Half of what it originally was. Equals what for the half-life? Let's set up the math on that before we use our calculator. Let's set up the math. Suggestions? Here's your model up here. No suggestions?
You mean the population of what?
We're looking for the number of days.
Oh, days.
The number of days for this wound. Here's my big old scrape on my elbow. Okay, big old wound. For it to get down to half as big as that.
So put in half for A of n.
Very good. Melissa's suggesting A of n, we don't know what it is. Well, we do know. We know it's half as about s. So A of n, we're going to let A of n be equal to half of the original value. And then that's going to be equal to, you look up at your model, A of n is taking on half of the A naught value. So over on the other side, it's equal to A naught e to the minus 0.35 n.
But half of that.
Well, here's the half. Here's the future value.
Okay.
This is A of n, in time in the future. N days into the future is half of what it started with, and that's equal to the original model, where n is going to take on this value that will be solved for here. What's
Time.
that number of
Amount of
days, n? Because what happens to the original value? What can we do in the algebra? Can't we divide both sides?
By A of O.
Yeah, by A naught. Divide both sides by A naught, and it disappears, doesn't it? So on both sides of this equation right here, divide both sides by it, it's gone. So the problem will turn into just a half being equal to that exponential expression. All right? Any questions on that? Folks are mighty quiet today. Maybe that's so that we get good audio transmission on the video, huh? Okay. Everybody go with me? Okay. What kind of an equation is this now? It's an exponential equation. And we need what to solve it? Okay. Sounds like a broken record, doesn't it? Take a logarithm of both sides, isolate the exponential. We got it isolated, see, by dividing by A naught, both sides. We got rid of this A naught here, and we now have the exponential isolated, and we're going to take logarithms on both sides, and we'll probably use Kyle's suggestion again, use natural logs like we did on the previous problem, because we even have a base E on this problem. So let's go up on the right side over here and go ahead and take that natural logarithm of both sides. So I'm gonna put my unknown on the left side. So I'm gonna take the natural log of this exponential expression, and that's the log of 1/2. Now why don't you folks take just a second, a couple of seconds, apply your power rule carefully, and then see if you can simplify using your quotient property over here on the right side. See if you can simplify the natural log of 1/2. And I'll be back just a second. Okay. What do you think? Tyler, you want to help me?
I'm so lost. I have no idea.
Uh-oh, we don't want to be lost.
Is it going to be ln?
Who else is lost? Anybody else? A couple of you, several of you, bunch of you. Okay, let's talk our way back through this for just a second before we go forward. I mean, there's no sense of being totally lost in the woods, otherwise you might get hypothermic or something. Okay, so let's go back to the problem. We're looking for how many days this population, the area of this wound is going to shrink down to half as big as it was. You have a math model right here. Here's our model. We want to let, this is the future value here, folks, where my hand is. This is the future value. This is the initial value. This exponential thing is what causes change to occur to the initial value. When you multiply the initial size of the wound by whatever number this is, it's going to cause this future value to change. So I'm talking to the folks that are confused. Okay, everybody okay with that? Okay, the question is how many days for that wound size to come down to half of what it started with? So as Melissa had suggested, this value, this future value here, becomes half of the original. So it's a simple substitution. You put in a half of the original value right here. So half of the original value, here it is right here. Half of the original value is equal to the original model. I hope that's all right with people. So here's the equation right here. Notice that both sides have this number in it, which is, I'm not giving you a number, it's just treated as a constant here. That's what the wound size was originally. If we divide both sides by that, that will turn to 1 and leaves a half sitting right here. Is everyone with me? Tyler, everybody with me now? Okay, good. So we get it down to this, and then when we say to ourselves, okay, well, where are we? We've got this exponential thing isolated. It's isolated, and it's equal to this nice old half. And then to solve an exponential equation, we always isolate the exponential, and then we take logarithms of both sides. We need to take the logarithm, use a logarithm base e, because we have a base e exponential. So this then leads us to this step up here. Camera? Thank you. Okay, so we get to this point. Is everybody together now? We all good? Now we have to remember some rules of logarithms, some properties. We have to take and apply the power rule. Power rule takes the logarithm of some exponential expression and lets that exponent pop out in front. That rule, that power rule, or power property, is really important because that's how you get an unknown exponent and make it solvable. It pops it out in front, becomes minus 0.35 n times the natural log of e is equal to the other side. We can now solve for n. When n is tied up inside here, up on the exponent, we can't solve for it easily. So that power rule is extremely important in solving exponential equations. It's essential. The right side of the equation, we want to use the quotient rule on it. Suggestions? Taylor, you have an idea?
ln 1 minus ln 2.
Good. Natural log of 1 minus the natural log of 2, your quotient rule. Natural log of 1 minus natural log of 2. Wish this board was a little larger. The log of a ratio becomes the difference in the logarithms. Now, let's tidy it up a little bit. What's e? Right where my finger is. The base is e. The exponent of e that gives you e is 1. Over here, the base is e. What's the exponent of e that gives you 1? E to the 0 equals 1. So the exponent of e that gives you 1 is 0. So what we get is a beginning algebra question now. Negative 0.35 n equals minus natural log of 2. Natural log of 2 is just a number. And multiplying both sides by negative 1, we get rid of that. And so it turns positive, and we end up with n is equal to the natural log of 2 over 0.35. Now, let's go ahead and let's use our calculator to this point and get these answers from the previous problem here. Where is it? Right here. we'll get these answers to see what happens to the size of the wound after 3 days. After 10 days, we'll get those answers, and we'll also figure out how many days it takes, approximately, for the wound size to become half of what it originally was. Okay, so we'll turn to the calculator now. And we could just do this on our normal calculator screen here. But a better way to probably do this is to go into our y equals screen and go ahead and put the function in. Well, actually, gonna have a little bit of a problem there because I don't know my initial amount, do I?
That's what I was gonna ask. Why can't we just solve for the initial amount and change the days?
Oh, Jennifer was asking, let's go back to the board for a second. She was asking, why can't we solve for the initial amount in this model? Look at the graph. Is there any information about the wound size? Big, huge scrape on my elbow, or just a little tiny nick? Anything about the wound size initially? Or how big the wound is after some period of time?
No.
No. This is a generalized problem, is what they've got going here. Okay? So we have to keep that A naught value in the problem, is the issue. Okay, so that was a good question. This math we're doing here isn't just for wounds, scrapes, okay? This is for any kind of decay stuff, like it could decay, like I mentioned earlier, or other kinds of decay models, okay, in application. Okay, so what we would have to do here, I think I'm just going to use the regular old calculator screen, is we're just going to punch this up as a number, and this is going to be some number times A naught for our answer. Similarly here, some number here times A naught. And so let's go ahead and get those. E to the minus 0.35 times 3. So we'll do this back here on the home screen. E to the negative 0.35 times 3. And we have that value. And while we're at it, let's punch E to the negative 0.35 times 10. And then, since we're looking at the screen here, let's go ahead and get that last answer, where we have natural log of 2 divided by 0.35. So now we have all of our answers that we need. Get 0.35 A naught for the wound size after 3 days. And the other one was after 10 days, 0.03 A naught after 10 days. And then the number of days for it to come down to half its size, it takes 1.98 days. To reduce to 1/2 the original size. All three answers. Okay, so if we come back up here to the model, my sketch, this graph actually is going to come down quicker than what I originally showed here. Let me see if I can be a little more accurate on the sketch. If this is 3 days and 10 days, look at this. After 3 days, folks, it's 35% as big as it was originally. It's about 1/3 after 3 days, healing pretty quickly. After 3 days, it's about 1/3 of what it originally was. Here's its original size. Here it is now after 3 days. And after 10 days, look at this. Completely healed up, aren't we? It's down to just 3%, little tiny scab. 3%.
Assuming that it wasn't A
of the
whole
original.
body burn or something.
Right, yeah, it could be a burns, and then there'd be a longer half-life for, say, a burn recovery kind of a thing. Okay, so 3%, and that's almost gonna be microscopic here after 10 days. So this thing's coming down pretty darn quick, which is nice. Okay, and then look at this, roughly 2 days, here's our 1.98 right there. It is half of it what it originally was. Half of what it originally was after 1.98 days. Okay, make sure you can do a problem like this. Very important. Okay. The last part of this second quarter in the book was how many days does it take for the wound to get down to 10% of its original size, 10% of the original size. So this future value here is going to become 0.1 of the original amount. And you can just track it in the math here. It would be, instead of this being a half here, 50%, it would be 0.1 right there. So it'd be the natural log of 0.1 divided by negative 0.35, and you get your answer. And 10% is going to be, this thing was down to 3% here, so 10% is going to be right in here somewhere. So this would be about 10% of the original amount, and it'd be some value of time in days right there. So if you have a sketch, I keep doing this throughout the course. I'm trying to get you to always draw a sketch if you can, because it'll give you insight then the kind of answers you get using your algebra skills. And you can catch mistakes, because if you mispunched your calculator and got something way off from something less than 3, then you knew you probably punched something wrong by having the understanding of the graph. Okay. Any questions? Those people that were confused earlier, does this make sense, more sense now? Okay, try to get it tied together through practice. Let's see if we can find another application model that would be useful. And actually, I think what we'll do is just go do some straight math, okay, for a second, because we need a little more practice on this. Some of you do. Let's take a question somewhat similar to what you probably had assigned in homework. Over on this board. Let's take a problem like this. Let's say we have the following. 0.3, this happens to be number 40 on page 311. 0.3 times 4 raised to the 0.2x is equal to 0.2. Again, it's an exponential equation. First step, isolate both sides, or excuse me, isolate the exponential. So 4 to the 0.2x is equal to
0.2 over 0.3.
0.2 over 0.3 reduces, does it not? 0.2 over 0.3 to 2/3, right? To 2/3. At this point, again, we're just going to take logarithms. Take logarithms of both sides. So I'm going to do it fairly quickly. I'm going to use base 10 logs. So I'm going to take log of 4 to the 0.2x equals the log of 2/3. The exponent pops out in front by the power property or rule. And then we're going to divide both sides by 0.2 log 4. So we're going to get the exact answer is the log of 2/3 divided by 0.2 log of 4. Now we could tidy this up a little bit or punch this straight away on our calculator. Keep in mind what 2/10 is. 2/10 is 1/5. 1/5 in the denominator turns into a multiplier of 5 on the numerator. This is 1/5 down here, turns into multiplying 5 on this logarithm up here. So another way of writing the exact answer would be 5 2/3 divided by log of 4. So these are your exact answers here. And your approximate answer, if somebody would punch that on their calculator carefully, you should practice using your calculator properly on these things. I have an answer.
Negative 1.462.
Ariel, anybody else get that?
I have that with negative.
We all should get the same answer, shouldn't we? Let's go back to the calculator. We're taking base 10 logarithms of 5, actually I need a 5 there first. 5 log of 2/3, and I'm dividing this by the log of 4. Negative negative 1.4624 approximately. How would we check this answer?
Plug it in.
Do what, Taylor?
Use the trace and
Plug it in where?
to the X value.
Back up in the very original question. In the very original question, we're going to take this answer, and I would store this in a memory cell. Tuck that into a memory cell, and then store it in a memory cell. Why don't I call it A for answer? And then we will the original to test to see if 0.3 times 4 raised to the 0.2a, is that equal to 0.2? Notice the question mark over the equal sign. So back to the calculator quickly. If I now store this in alpha A, and then I'm going to punch the original question, 0.3 times 4 raised to the, in parentheses on the exponent, folks, this is important, 0.2 alpha A, I get a value of 0.2, and notice that's exactly equal to the right side of the equation. A quick check. Okay, we have time to solve quickly a logarithm problem. To do is to take a problem like number 29 and see if we can zip through that. Number 29.
It's 29 on page
Oh, I'm
12.
sorry. We're on page 311. Page 311 happens to be the log base 1/3. Of x squared plus x. And then we are subtracting from it the log base 1/3 of x squared minus x. And that is equal to -1. -1. Okay, this is obviously a logarithm equation. I have not spent any time with you on logarithms that are smaller than 1, whose base is smaller than 1. But here's one. And all you do is just use the same math that we've been doing. Same math we've been doing. So what we do is notice we have a logarithm minus another logarithm, same bases. So that collapses, doesn't it? By the quotient rule into a single logarithm. Base 1/3 of x squared plus x divided by minus x. Log of a difference, or difference of logarithms, becomes the log of the ratio. And that's equal to -1. We have isolated the logarithm, which is necessary. So we've isolated it. Next step. You should be getting good at this. Write it in exponential form. The exponent is a logarithm. We said that about 1,000 times. Happens to be -1. The exponent is -1, the base is 1/3. So 1/3 to the -1 power is equal to the argument inside this logarithm. And something to the 1/3 power, or excuse me, something to the -1 power is the reciprocal, isn't it? It's this result on the right. That's a nice old 3, isn't it? So now we have an algebraic equation. It happens to be a fractional quadratic equation. We multiply both sides by the denominator. And on the left, we will get x squared plus x. And on the right side, we get 3 times x squared minus x. Don't make a intermediate algebra error at this point. After all this work, what do you now do?
You expand that and
You have,
everything on one side.
like Diana said, you have to expand this, you have to distribute the 3, and then you have to move, since it's a quadratic equation, you move everything over to one side and put it in the form that you use to solve quadratic equations. So we have just a short.
Can't we factor out an x way back at, yeah.
You got to be careful about that. Let's go ahead and just keep rolling here for a second. So we see a 3x squared minus 3x on the right. And so let me move everything over to the right side. So I get 2x squared by subtracting x squared from both sides. I get 2x squared. And then I have minus 3x over here, and I subtract x from both sides, and I get minus 4x. And that's all equal to 0. I think what you were suggesting, Melissa, was maybe back earlier on, maybe back here, is factoring out an x and reducing it out. What happens, be very careful about that. You don't ever want to remove, through division or canceling, you don't ever want to remove your variable, because you lose a possible answer that way. Okay, so just follow the algebra right on through. We get it down to this. Now at this point, a common 2x comes out, and we're left with x minus 2 there, equals 0. And what answers do we get by our 0 product rule?
0.
X equals 0, or x equals 2. Now, we're not done, because if you go back now and check these answers, let's try putting 0 back into the original question. We're talking about a log base 1/3 of 0. Does a logarithm of 0 exist? Think about a logarithm's graph. Does a logarithm of 0 exist? No. That's a vertical asymptote. Log of 0 does not exist. So this is a discarded extraneous root. And then if we put 2 in, let's check. So log base 1/3 on the original of 2 going in here is 4 plus 2 is 6. And then we're subtracting from that the log base 1/3 of 2 going in here is 4 minus 2 is 2. Is that equal to -1? What I would do is collapse this into a single logarithm. Log base 1/3 of 6 over 2, because we have the subtraction of the logs, becomes 6 divided by 2 is 3. Is that equal to -1? Is that equal to -1? And then what we do is write this in its exponent form. The exponent is -1, so 1/3 to the -1, is that equal to 3? On that note, 3 equals 3. We're feeling good. So that takes care of practice of solving both exponential and logarithm types of equations. Okay, that's it for today. We'll meet you in the computer lab tomorrow at 10 o'clock, and bring your homework folders with you. I want to collect your homework up through, I think I said the exam covers up through 5.3. Didn't I say 5.3?